Welcome to the deep dive. Today we're really getting into the foundations, looking at how computers actually represent numbers.
Right, specifically integers and floating point numbers. It's fundamental stuff.
Exactly. And, it might sound super technical up front, but honestly, understanding this is like getting a peek under the hood of, well, almost all modern technology. There are definitely some aha moments coming up.
For sure. And we're mainly drawing from Hello Algo, specifically the section on number encoding. It gives a really solid base for both integer and float representations.
Perfect. So our goal today really is to give you a deep, kind of lasting understanding of this. It's not just trivia, it's knowledge that helps demystify what's happening inside the machine. Oh, okay. Let's dive in. Integers first. How do computers even start representing whole numbers?
Well, it all starts with binary, right? Base 2, just zeros and ones. That's the computer's native language. Representing integers, the whole numbers, is kind of the first hurdle. Hello Algo lays out three main ways computers have handled this, especially dealing with negative numbers.
Right.
Sign magnitude, one's complement, and the big one, two's complement.
Okay, sign magnitude. That sounds, well, pretty obvious maybe. Like one bit for the sign, the rest for the number.
Yeah, exactly. The leftmost bit tells you 0 means positive, 1 means negative, simple enough. And the other bits just, represent the value, the magnitude. It feels intuitive.
It does, but Hello Algo points out it's not great for actually doing math, is it?
Not really. That initial simplicity causes headaches. You
Yeah.
take 1 plus, easy for us, should be mag@1. But in 8-bit sign magnitude, 1 is what? 00001, and magnitude is 70001.
Okay.
If you just add those binary patterns like the computer might naively do, you get 1000,0001.
And that in sign magnitude means...
It means a -3, which is
Yeah.
wrong, clearly
Yeah,
wrong.
yeah.
So yeah, simple idea, but it breaks down with arithmetic.
Yikes. Okay, not good if you want, correct answers.
Yeah.
So what came next?
Yeah.
How did they try to fix that?
The next step was one's complement. Now, for positive numbers, it's exactly the same as sign magnitude. Still, 000000001 for positive 1.
Good.
The difference is how it handles negative numbers. To get the one's complement negative, you take the positive version and just flip every bit. All of them, including the sign bit.
Flip every single bit. Okay, so for -2, positive 2 is 000000000.
Right.
Flip all those bits, you get 11111101. That's -2 in one's complement.
Okay, so let's try our 1 plus the -2 again. That's 0000001 plus 11111101.
Exactly. Add them up using binary addition, and you get 11111111.
And what's that if we convert it back?
Well, if you reverse the ones complement process for negatives, flip all the bits again. 11111110 becomes 000000001. And remembering the original sign bit was 1 for negative, that translates back to -1.
Ah, it worked. Okay, so one's complement seems like a definite improvement for calculations then.
It is for that specific problem anyway.
Right.
But as Hello Algo points out, it still has this kind of weird quirk. Ooh, what's that?
It has two ways to represent 0. You have your normal all zeros, 000000000. That's positive 0.
Right.
But if you follow the rule for negatives, take positive 0 and flip all the bits, what do you get?
Flip all zeros, you get all ones. 11111111.
Exactly, and that's -0 in one's complement.
Yeah.
Two different bit patterns for the same value, 0.
Yeah, that seems inefficient and potentially confusing for the computer's logic.
It is. It adds complexity to the hardware because it has to recognize that these two different things actually mean the same number. You want things simple and unambiguous if possible.
Okay, so that brings us to the third method,
Well,
the one computers actually use now, right? Two's complement.
that's the one. Two's complement, again, positive numbers, same as before. 000000001 is still 1.
Okay, consistent so far. How does it handle negatives differently?
It builds directly on one's complement. To get the two's complement negative, you first find the one's complement version, flip all the bits, and then you add 1.
Add 1. Okay, so for -2, the ones complement was 11111101.
Right? Add 1 to that binary number. You get 11111110. That is -2 and 2's complement.
Interesting. So what happens to our -0 problem? One's complement -0 was 11111111.
Add 1 to that.
111111 plus 1. That gives 10000000. Like, it overflows.
Exactly. And since we're working with a fixed number of bits, say 8 bits,
Yeah.
that leading 1 that overflows just gets discarded.
So -0 becomes 000000000.
Precisely. Same as positive 0. Problem solved. 2's complement has only one representation for 0. Much cleaner.
That is neat. Very elegant. Okay, now, something else Hello Algo mentioned. The range. For, like, An 8-bit byte, its unishes 128 to 127. Why isn't it symmetrical? Like a nice 127 to 127.
Yeah.
Where does 128 come from?
Yeah, that asymmetry is a direct result of how 2's complement works and having only one zero. Think about 8 bits again. 0 is 0, 0, 0, 0, 0, 0, 0, 0, 0.
I like that.
Positive numbers use the patterns starting with 0. So 0, 0, 0, 0, 0, 0, 0, 1 is 1, up to 0, 11, 11, 1, 11, 11.
Which is 127. Okay.
Now, negatives start with 1. We saw 11, 11, 11, 11 is next 1. If you keep going down, 1,000, 0, 0, 0, 0, 1 is next, and 0, 7.
Okay, following that.
Yeah.
What's left? There's one pattern we haven't assigned a meaning to yet, starting with 1.
Exactly. The pattern 1,000, 0, 0, 0. What value should that have?
Oh.
If you try to apply the 2's complement rule in reverse subtract 1, then flip the bits, you don't actually get a positive number within the 8-bit system that corresponds cleanly.
Ah, so it's kind of unique. It doesn't have a positive partner in the same way negative 1 has +1 or negative 127 has plus 127.
That's the essence of it. So instead of wasting this pattern, the designers assigned it the next most negative value, which is negative 128.
So it fills the gap and uses all the patterns.
It does, and it works mathematically within the system. Hello algo shows if you add negative 127, which is our negative 0, 0, 0, 1, and negative 1, which is 11, 11, 8, 11, using 2's complement addition, you get 1,000, 0, 0, 0, 0, which is our negative 128. It all fits together.
Wow. That's actually really clever, maximizing every bit pattern. And Hello Algo really stressed the why behind using 2's complement. It's about the hardware, right? Making things simpler.
Hugely important. The absolute killer feature of 2's complement is that the same electronic circuits that do binary addition for positive numbers can also handle subtraction and addition involving negative numbers without any changes.
How does that work?
Because subtracting B from A is identical to adding the 2's complement of B to A plus B. You just need circuitry to calculate the 2's complement, which is just bit flipping and adding one, relatively simple operations, and then you reuse your main adder circuit.
So you don't need a whole separate chunk of hardware just for subtraction.
Exactly. You save space, complexity, and potentially power. It streamlines the processor design enormously. And then more complex things like multiplication and division can often be built up from sequences of additions, subtractions, and bit shifts. So simplifying addition is a massive win, especially crucial back when hardware resources were much more constrained.
That makes total sense. It's not just about representing numbers, it's about making the computation efficient. Okay, brilliant. Integer encoding feels much clearer now. Let's switch gears then. What about numbers with decimal points? Floating point numbers, the standard float.
Right, the IEEE 754 standard stuff.
Yeah, and the thing that always got me is a standard int and a standard float often use the same amount of memory, right? Like 4 bytes, 32 bits.
Often, yes.
But the float can represent this astronomically larger range of values. How does it squeeze so much more range out of the same number of bits?
That's the million-dollar question. And the answer is it uses those 32 bits very differently. It's a completely different strategy than integer encoding. Instead of just sign and magnitude, a 32-bit float is divided into 3 specific parts.
3 parts, okay.
You have a sign bit, this is just 1 bit. Then you have an exponent field, e, that takes up 8 bits. And finally, a fraction field, n, which gets the remaining 23 bits, sometimes called the mantissa or significant.
Okay, sign, exponent, fraction. That exponent part sounds important for the range thing.
It absolutely is. That's the key. Hello algo gives the formula to piece it all together. The value of the float is calculated as -1 raised to the power of s.
So -1s gives the sign positive or negative. Makes sense.
Times 2 raised to the power of e minus 127.
Whoa, okay. E minus 127, why subtract 127?
That's called the exponent bias. Those 8 bits for e can represent unsigned integers from 0 to 255. By subtracting a bias, in this case 127, the actual exponent value can range from -127 up to +128, effectively. This lets you represent both very small fractions, negative exponents, and very large numbers, positive exponents, without needing a separate sign bit just for the exponent. It's a clever trick.
Ah, okay. So the 8 bits store a biased exponent, and we unbias it by subtracting 127. Got it. And the last part of the formula?
Times 1 plus n.
1 plus n, where n is the fraction field, while the 1 plus n.
Good question. N is the 23 bits representing the fractional part, the digits after the binary point. For most numbers, called normal numbers, there's an implicit leading 1 assumed before the binary point. Think of scientific notation like 1.23 by 105. That leading 1 is always there. Binary floating point does something similar with an implicit leading 1, followed by the fraction n. So the actual value being scaled by the exponent is 1 plus n.
So the 23 bits only store the part after the binary point, because the 1 part is just assumed.
For normal numbers, yes. It effectively gives you an extra bit of precision for free. Hello Algo has an example. Figure 3.5. Let's say S is 0, positive, E is 124, and the fraction n represents 0.375 in decimal, which is 0.011 in binary.
Okay.
The calculation would be manic 10, 2, 124, 127, 1 plus 0.375.
Which is 1, 2, 3, 1.375.
Right, and 2, 3 is 18 or 0.125, so 0.125 times 1.375. That's how it encodes a fractional value using these parts.
I see. So you have the sign, the exponent giving you the scale, big or small, and the fraction giving you the precise value within that scale, with that implicit 1 helping out. That structure definitely explains the range. That 2E127 part can get huge or tiny. Hello, Algo mentioned a max value around 3.4 times 10 to the 38.
Yeah, something like that. That 8-bit exponent, even with the bias, gives you a massive range compared to just representing the magnitude directly like an integer does. But, and this is a big but.
There's always a catch, isn't there?
There is. This huge range comes at the cost of precision.
A loss of precision. What does that mean exactly? It can't represent every number accurately.
Exactly. Integers are perfectly precise. Within its range, every integer has an exact representation. But with floats, because you only have those 23 bits for the fraction plus the implicit 1, you can't represent every possible number between, say, 1.0 and 2.0. There are gaps. Yes. And the size of those gaps gets bigger as the numbers themselves get bigger. The difference between two consecutive representable floating point numbers increases as the magnitude increases because the exponent changes the scale.
So for very large numbers, there might be loads of whole numbers, integers, that just can't be represented exactly as a float. They fall into those gaps.
Precisely. It's a trade-off. Range versus precision. You get vastly more range, but you lose the guarantee that every number within that range is perfectly representable.
Okay, that's a crucial difference. Now, Hello Algo also mentioned special cases for the exponent e, when e is all zeros or all ones, E00, E255.
Right, those exponent values are reserved for special meanings. They don't follow the standard calculation. If e is 0 and the fraction n is also all zeros, that represents 0. It can be plus 0 or not 0 depending on the sign bit s.
Okay, 0 makes sense. What if E0 but n is not 0?
Then you get what are called subnormal or denormalized numbers. These are very small numbers, even smaller than the smallest normal number you can make. They use a slightly different formula, basically losing the implicit 1 to get even closer to 0.
Why have those?
They help bridge the gap between the smallest normal number and 0. It allows for more gradual underflow, essentially improving precision for results that are extremely tiny, right down near 0. The smallest positive normal float is about 2,126, but the smallest subnormal is way smaller, like 2,149.
Interesting. So it's like an extra gear for really tiny values.
Mm-hmm.
Okay, what about the other end? When e is all ones, E255.
If E255 and the fraction n is all zeros, that represents infinity, plus or minus infinity, again, depending on the sign bit s.
Infinity, like if you divide by 0...
That's one way you might get it, yes.
Right.
Or if a calculation results in a number too large to represent.
And if E255 and n is not 0...
That represents nan, not a number.
Not a number.
Yeah, nan. It's the result of invalid operations, things that don't produce a real number result, like taking the square root of a negative number, or maybe 0, 0. It's a way for the system to flag that the result isn't meaningful in a standard numerical sense.
Got it. So these special values handle exceptions and edge cases like 0, infinity, and invalid results. And briefly, double precision floats, just more bits.
Pretty much, yeah. Double typically uses 64 bits. More bits for the exponent, I think 11, and way more for the fraction, like 52 bits.
So same principles, just bigger, wider range, and better precision.
Exactly. More bits mean you can represent an even larger range of exponents and store many more significant digits in the fraction, reducing those gaps between representable numbers.
Okay, wow. This has been, well, genuinely enlightening, going from sign magnitude's simple idea to the cleverness of 2's complement for integers, and then seeing the totally different strategy of floats with their sign, exponent, and fraction. It's pretty amazing engineering.
It really is. When you dig into it, you see the ingenuity involved in taking the continuous world of mathematics and mapping it onto the discrete, finite world of binary bits. Understanding these encodings gives you a much deeper feel for how computation actually works.
Absolutely. It explains why certain things behave the way they do in programming, why some calculations might have tiny errors, why data types matter so much. It's foundational.
Definitely foundational. These choices about number representation were made decades ago, but they still underpin almost everything we do with computers today.
So maybe a final thought for everyone listening. Now that you have this insight into how fundamentally different integer and floating point representations are, how might that change how you think about, say, choosing data types in your code? Or perhaps understanding potential pitfalls in calculations involving very large or very small numbers? Or even just appreciating the history of computer design?
Yeah, what other simple-seeming digital concepts might have these really intricate, clever solutions hiding underneath? Maybe it sparks some curiosity about, I don't know, how characters are encoded or even error correction codes.
Exactly. It might even make you think about things like how floating point errors can sometimes accumulate in complex simulations. There's always another layer, another fascinating detail, just waiting to be uncovered. Thank you for joining us on this deep dive.